Any ray going parallel to the principal axis will go via the principal focus after reflection. So this is the diagram of that activity which you performed of sun rays falling on a concave mirror and the piece of paper being at the principal focus. How do you draw this diagram? For a concave, for a convex mirror. Alright, so let us do the same thing. Let's find out the center of curvature, let's find the pole, focus, etc., and the image formation for a convex mirror. This was concave mirror. Okay, this was concave mirror. And this, the distance, the last thing to define is the distance between pole and the focus. This distance is called focal length of the mirror. A very, very important aspect of a mirror. So this is the focal length, and this is the way we always find the focal length. But that focal length, remember, is not exact; it is approximate. So if I told you to find the approximate focal length of a concave mirror, this is the activity that you do, and you will measure the distance from the mirror to the paper where it burns, and the distance is approximate focal. So this was your concave mirror. Now let's study similar things happening in a convex mirror. Okay, convex mirror. How do I draw it? From where? Alright, so I'll draw it like this. Shade it on this side because the polishing side will be this, and polished side will have the rays reflecting from it. Important thing to note. You tend to draw the center of curvature, put the center of curvature here, put the focal length somewhere here, etc., etc. Be very careful. Nothing doing. What you have to do is, remember, since this is the sphere, center of curvature would lie somewhere here. The pole remains the central point of the midpoint of the mirror. The line joining the pole and the center of curvature extended on either side is called the principal axis as before. Now let the rays of the sun come parallel to the principal axis. I have to draw a ray diagram. I have to draw the normal at the point of incidence. So at this point, if I have to draw the normal, I have to join with the center of curvature. Why am I drawing it shaded? Extend it on the side. Why is it drawn shaded? Because this is not a ray, it doesn't exist. We are drawing it only for our convenience. Therefore, it has to be shaded. There is a lot of importance to this fact as to what lines are solid and what lines are shaded. Coming back to this, angle of incidence is angle between the incident ray and the normal. Now, where would the ray go after reflection? It will follow laws of reflection as usual, and therefore, it will go on the other side here, such that the angle of incidence and angle of reflection are equal. Similarly, I do the same thing here. I have to join this with the center of curvature, call this as angle of incidence, this and this will be equal, and this is the second ray, this is angle of reflection. So these are the two rays, ray 1 reflected ray, ray 2 reflected ray. Well, is there any hope of their meeting this side somewhere so that they make an image? I told you before that whenever the reflected rays intersect, the image is formed. Are they going to reflect somewhere? They are going to intersect somewhere on this side? No chance, because they are diverging rays. And therefore, they will meet at a point somewhere here. I am again drawing it dotted, right? And this point will be called as focus. There is a principal focus or focus. Now, there is obviously a mistake here. The reason being, the center of curvature, the principal focus lies exactly midway. In most spatial cases, it lies midway between the pole and the center of curvature. And in my diagram, it doesn't show this. So how do we draw the diagram so that we don't make this mistake? I'll explain to you again, once again. Let center of curvature be there, wherever it is. Your angle of reflection has to be the way it was. Choose the focus first. If this is center, choose the focus midway. Approximately, these distances are equal. Then, draw the normal at the point of incidence. Let the ray Now this ray has to reflect in the direction such that it, when extended backwards, will meet at F. Therefore, I have a direction in which it will reflect. Alright, I join this dotted, join this, and with a scale extend it in this direction. This is the way the ray will reflect, and this will automatically R will be equal to I. Similarly, join here. This is officially, I am cheating, right, but I am making the right diagram. So the ray will reflect in this direction, solid line, and the normal will be somewhere in between. The normal here will be, this is the normal. So at this point this will be the normal. Okay, and the ray is going on this side, this is R. Now this diagram is correct. I defined center of curvature earlier. It is the center of the sphere of which the convex mirror makes a part. Pole is the midpoint. How do I define focus in this case? The definition goes as follows. If a ray of light parallel to the principal axis strikes the mirror at a point, then it is reflected in such a direction that when extended backwards, it seems to be diverging from a point on the principal axis. This point is called as the principal focus. Alright, so you have this kind of diagram, and you cannot keep a piece of paper here and make it burn by the sun rays. Think about it, why not? Shall I tell you? Because the rays are actually not meeting here. The rays are going in this direction, so all the heat of the sun would be on this side. Nothing really is coming on this side. Remember, it is an opaque object. This mirror is not transparent. It's an opaque object. So you would not have any rays here at all. These are just the points that we are considering. We know these points exist, but they are points in space. They are not really on the mirror, or you don't come in touch of those points. So this is how we draw the diagram for a convex mirror, and again here the distance between the principal focus and the pole will be called as the focal length of a convex mirror. Okay. Now, as I said, in special cases, the radius of curvature is twice the focal length, or the center of curvature is double the distance of the focal length. Okay, our focus lies between the pole and the center of curvature.